Now, base 10 will need 10 spaces for you to read each number in that string. Base 2 will need 2 spaces. Now, in base 2, those 2 spaces can only be one of 2 values. Both can be zeros, both can be 1, it can be 1 0 or 0 1. 4 combinations in base 2 can have 4 combinations of arrangement of those 0 and 1 in base 2 because you're using 2 positions. Each position is a 0 and 1. That's one position. It can be one of those 2. And the second position can be 1 or 0 2. And the 2 of them form a word 2-bit wide. Now, in decimal, you will need a word 10-bit wide because it can be 0 through 9. Now, in the units column, it can be 0 or it can be 9. In the 9 column, it can be 9 or 0 at the bottom, right? So that's a square 10 by 10, 100. You can have 100 different positions. So how do you know what each position is when you do an operation? It's anywhere in that box, any one of those 100 spaces. 0 to 9, it can be any one of them. In base 2, it can be only 0 or 1, whatever combination. So now the idea is that if you use base 10, you would need less circuitry. That's what I think. So now, if that is true, and you can use light and base 10, then you can use on and off in base 10 too. And they already have on and off in base 10. In base 2, they already have on and off. The old circuits are all on and off. The ALUs and the memories, they're set up for base 2, but how they're set up internally, I really don't know. But from what I saw, addressable RAMs, you can go to a position, pick a 0 or 1. Now, when you have a base 10 memory, what is in that memory? What is in that register position? So in a way, if you can use in a binary system 0 or 1, you go there, it's a 0, and you go there, it's a 1, for 2 operations in parallel at the same clock cycle. The same time 2 instructions are going through, one operation sees a 0 in that position, the other operation sees a 1 in that position. That would be almost like quantum. Now, if you can do that for decimal system, you go to that position, it's either 0 or 1 or 2, depending on what the operation gives, then you have a quantum computer there too. Is that possible or not? Now, if you're able to see that, then you can understand if that happens, it's a quantum computer beyond what we have in the solid state integrated circuits now. And this quantum computer that I'm thinking of in theory is also an integrated circuit solid state. I say if you're able to use it in base 10, you will cut out a lot of mapping and manipulations and conversions and stuff like that. Is that so or not? And if you can use light to do that, you can use binary digit too, 0 and 1. But where that 0 and 1 is will tell you if it's a 9, a 0, it's a 9 or not a 9. If it's a 0, it's a 9. If it's a 1, it's a 0. You can be able to identify it that way too, right? You'll need you have 10 positions, 2 to the 3, you'll need 4 bits to tell you what that position is. So you'll have to have 4 binary bits keeping track of each decimal position. That should make it simpler, right? And cut down a lot of steps, right? And that would be easy. You can use the existing components. You just rewire it. You rewire the hardware, you redesign the hardware, convert the hardware for base 10. And you can do that by having the same binary bit 0 and 1, and where they are in the register will tell you, if it's a 1 or a 2 or a 9. And then you have 4 bits, 4 binary bits will tell you what is the value of that position where it is. So say you have in the 9th cell, right? You have a 1 there. If there is a 1, there is something there. If there is a 0, there is nothing there. If there is a 0, you can just know that there is nothing there. So you know what it is. It's a 0. If it's a 1, it can be one of the 9 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, which one is it? You will need 4 bits to tell you which one it is. Now, if you do that in the front end, then you'll cut out a lot in the middle. Then you do that in the back end too. By that I mean you will have your input 0 through 9 as rows coming in, and the 4 bits will tell you, on the column will tell you, what is the value of that position Where the ninth row is, it can be anything from 0 to 9. Where the first row is, it can be anything from 1 to 9 in each box, right? So you will need 4 bits to tell you what is the value of that position in that box. Will that work? I guess if photonic computers will work, then this will work too. This adds one step, one component, an interpreter, namely a 4-bit binary interpreter for each position.